Boys and girls, ladies and gentlemen, markers, everyone, welcome to Electrical Resistance, my ENGG104 YouTube video, I being Christopher Thurban. So to start off with, what is electrical resistance? Well, resistance is the opposition to the flow of electric current. In a circuit, the higher resistance means less electric current can flow. A common analogy is a water analogy. In the picture to the right, you can see water flowing through a hose, and the hose with the kink in it has a higher resistance. And so in the second half, there is a smaller arrow to denote a smaller current. Next up, how do we calculate resistance? Well, we can start with the equation R equals rho L on A, where R is resistance in ohms, rho is the electrical resistivity in ohm meters, and L is the length in meters, with A being the cross-sectional area in meters squared. Everything in the equation is pretty well understood by everyone other than rho, the electrical resistivity. So what is electrical resistivity? Well, resistivity is how well a material can conduct electricity, this meaning that materials with low resistivities make very good conductors, and materials with high resistivities make very good insulators. Now that we know what everything is, let's find out the resistance of a wire. Here, we have a coil of constant wire of length 2 meters that has a cross-sectional area of 7 times 10 to the negative 7 meters squared. If its resistivity is 49 times 10 to the negative 8 ohm meters, find its resistance. So, where do we start? With the equation, of course, R equals rho L on A. The question tells us the resistivity is 49 times 10 to the negative 8, the length is 2 meters, and the cross-sectional area is 7 times 10 to the negative 7 meters squared. So, put that in our equation, and now it's pretty easy. We just shove it all in the calculator, and what should come out is 1.4 ohms. Well, so we've now learnt the bulk of what resistance is, and how to calculate it. There's just one more thing we have to go over. Resistance is also altered by the temperature it's operating at. This can be factored in as an addition to our older equation. We now have R equals rho L on A times by 1 plus alpha outside of T minus T reference. Alpha in this equation is the temperature coefficient of the material, which is unitless. T is the operating temperature in degrees Celsius, and T reference is the reference temperature in degrees Celsius, this being the temperature at which rho was measured. This is almost always room temperature, 20 degrees Celsius. Most materials have a positive temperature coefficient, and their resistance increases with increasing temperature. However, there are a few materials with a negative temperature coefficient, and their resistance decreases with temperature. And that brings us to the end. Now you should know all about resistance and be able to apply it when needed. Thanks for watching.